Hi everyone, welcome back to another Adoptium webinar. I'm Ludmila Muiña, your host today, and I'm here to introduce our guest speaker, Thanos Strategopoulos, sorry about that, who will be presenting about GPU accelerated Java with TornadoVM and Temurin JDK 21. If you have any questions, please feel free to put it in the chat box or in the Ask a Question tab. And thank you for being here. Over to you, Thanos. Thank you.
Thank you very much. And thank you for the invitation and for this opportunity. So it is a great pleasure for me to present TornadoVM, our in-house project that we have developed at the University of Manchester. It is running for almost a decade. And I'm very excited to show you today how it can work with Temurin JDK 21 and what we can actually bring up together in the Java ecosystem. So I hope it will be interesting for you. A little bit information about myself. So I'm a research fellow at the University of Manchester. I have been working with the TornadoVM team on TornadoVM for the past 7 years. And my background is on compilers and hardware architecture. I have a background on FPGAs and GPUs. And I have worked also on cloud deployments of TornadoVM on AWS instances. So here are the details about me if you want to contact me or follow me in social media. And let's jump into the agenda for today. So what we have prepared for you. A little bit of a brief history about the project, and then we will jump into the actual overview of TornadoVM, what it is and what enables. We will have a view about the off-heap data types that we have created in TornadoVM. Then information about how you can set it up, which has become easily now with the SDK distribution. Later, we will jump into the actual integration in Java projects. I think this can be very interesting for Java developers. And finally, we will, before we close the webinar, we will show you the demos that we have with more complex cases, including an LLM engine that we have created and will run locally on my laptop on the M4 that I have right now. So let's start. Here's a little bit of history of TornadoVM. So it all started at the University of Manchester back in 2017. It was a research project, a PhD research project that was led by one PhD student, James Clarkson. And back then, the research question was, okay, what are the factors that can impact GPU acceleration for JVM, and particularly the Java programming language? So back then, we had this kind of research question, and many years later, we have an answer. We have developed TornadoVM. It has emerged. In 2018, we open sourced the project and we have transitioned to the Graal compiler. This gives the opportunity for TornadoVM to capitalize on Graal. So we can leverage specific optimizations that are coming from Graal. And in a sense, we extend the Graal compiler with more phases that enables us to generate code, parallel code, that can run on different hardware accelerators like GPUs, FPGAs, and even also multi-core CPUs like ARM, RISC-V, and Intel. So since 2018, we have 23 releases, and currently we are at version 2.2.0. We have more than 30 contributors in GitHub who have contributed in the project. And last year, we had our first production deployment at the European Space Agency Gaia mission. This is a collaboration that we have performed with the University of Geneva and SEDNAI, and it is developed under the project, the European funded project Aero. The idea is that data are coming from space and they want to analyze them, so data analytics, of high scale of data, and they have created some algorithms that they are parallelizing with the TornadoVM API, and they are able to run it on GPUs, and hence they can use hardware acceleration for that, and they can minimize the execution time. Okay, if we have a general scope of the project, we have put it in this slide at the center. We have TornadoVM. On the one side, we have the actual hardware backends that enables us to target different hardware devices and from different vendors. We have currently support for 3 backends. One is OpenCL. The second is NVIDIA CUDA PTX. And the third is SPIR-V, which is a binary format. And we are also working on adding support for Metal to run natively on Apple systems. On the other side, we have the JDK distributions that we have tested TornadoVM. As you see, we are compatible with different vendors and different distributions, included Eclipse Temurin that I will show you today in the demos. And we have support for JDK 21 if you are using the current SDKs, but we are also working on compatibility with JDK 25. And in fact, hopefully soon, in a couple of weeks, we will have a new release that we will be able to run with JDK 25. Apart from that, as I said, we are capitalizing on Graal. So we are able, through Graal VM and the Truffle framework, to be interoperable with other programming languages that can run on top of Truffle, on top of the Graal VM. So in this scenario, we could have, because TornadoVM API is a Java API, we can implement parallel implementations using Java and the TornadoVM API, and we can invoke them from any other programming language like JavaScript, Python, R, Ruby that are running on Graal VM. Now, in every release, we are also releasing Docker images, and we push them in Docker Hub. So we have Docker images for Intel and NVIDIA hardware that someone can use. And we have developed a set of proprietary, let's say, tools that are open source, like TornadoVM Pulse, that we maintain it, and in a sense, it can be useful for performance analysis of TornadoVM applications. We have Tornado Visualizer that enables the visualization of the generated bytecodes from TornadoVM. We have an IDE plugin for the IntelliJ called Tornado Insight, and I will show you later how it works. And it can also be used with other third-party tools like the NVIDIA Insight system or the Intel VTune profiler as well for more fine-grained analysis. And our project has been indirectly integrated with Quarkus and LangChain4j. And at the end of this webinar, you will have a flavor of this. Okay, let's start with a question. This question comes mainly from the beginning of the project. How much different is GPU programming, especially if we consider the perspective of a Java developer? So the answer is that it is very different. And here is an abstract view of what is inside our computers, even right now on the computer that I'm sharing. We have a multi-core CPU, we have the system memory, but then we can have also exotic hardware like GPUs and FPGAs, which are plugged through PCI Express or any other interconnect. And the idea is that they will offload computation from the CPU in a way that we can achieve efficiency. Okay, but we are Java developers. We have used to having some APIs that are very useful to express parallelism in our applications, like the vector API, parallel streams, and virtual threads. But they're mainly focusing on CPU side. So then the question is how we can target the other side, the exotic hardware. So if we consider the GPUs, a hardware engineer needs to start thinking differently in order to express the computation and utilize all this capacity of the CUDA cores that are available in NVIDIA GPUs, for example. So in this case, they have to start thinking differently. They start to express the computation at the thread level or per core, let's say. And not only that, but they also need to think how they will deploy on the GPU, because they may need to group the threads together in order to leverage the caches that are available, the cache memory, so that to efficiently access the data in the memory. And this is something that ideally Java developers, they don't need to do. And it is completely different from the way that we have used to it. So some key remarks about it. GPU programming requires a different mindset than the one that we have used to. The programmers must be familiar with thread level programming and the grids. The grid is a notion for actually deploying on the actual hardware that is available on the system. And there's a lot of verbosity. I didn't show you here, but we have a talk in DevOps that we go through an example and how someone can create a GPU program from scratch. And there is a lot of verbosity because everything needs to be explicitly defined. For example, the developers, they need to allocate some buffers to add the data that they want to process. Then explicitly, they need to create some low-level objects like command queues and contexts. And then they need to actually push the actual data, the buffers, into the command queues, fetch them, issue the actual process to start running, and finally get the result back. So this is something that actually breaks the abstraction that we have from Java, where we can reflect on the actual slogan, write once, run anywhere. So this breaks if we are considering the expansion of GPUs. Okay, so regarding TornadoVM, an overview. TornadoVM has been developed to address this problem. In a sense, it aims to expose a Java API for developers that enables them to access GPUs, but in a platform-agnostic manner. So the API has been developed in a way that Java programmers, they don't need to know how to program GPUs. They don't need to know how to program FPGAs. Instead, at runtime, the system provides the infrastructure to be able to JIT compile Java methods and to run them efficiently on the hardware. So at runtime, we have runtime features, but also we have a JIT compiler that can optimize the Java methods and to run on GPUs and FPGAs. Additionally, we are one of the first adopters of Panama, Project Panama. So we have developed some data types that enable users to allocate data off heap with a foreign function in memory API. I think this gives a great pass to show you some of these data types. So if you see my screen, I have a code snippet of a main method where a developer allocates data. In this case, we're creating objects. They are arrays of float type, so primitive type. And these data are allocated on heap. Then we randomize the input, and then we actually invoke the matrix multiplication. So these data are allocated on heap, and they are pruned to GC, garbage collection. Now, if we want to actually transition, migrate this implementation with off-heap data using TornadoVM, we will have something like this. As we see here, the TornadoVM API provides a collection of types. In this case, we have the float array, which is an object that inside it abstracts the memory segment that we are using for the Panama integration. And we can allocate the number of elements as we have here. So this is a one-to-one mapping of the transition from off-heap to on-heap data. Similarly, in order to set the data, we have some set and get methods, and then we can actually invoke the computation with off-heap data. So this gives you the idea how someone can migrate and use off-heap data if they have a lot of data and they don't want to be triggering GC often. And we have this website So in the docs of TornadoVM, you can find more information about this kind of changes that you need to do. The interesting part is that if you have a Java application and you don't want to change the data types, you can actually migrate data. So we have some factoring methods that enable the migration of your on-heap data to off-heap data types. And this is very useful. And we have also the opposite, some from off-heap data to go back to on-heap data types if it is needed. And this is also available in the same link. I think the most interesting part is that even if you don't want to use hardware acceleration, you can use the API in order to use the off-heap data, which is a useful feature. Excellent. Let's jump to the next part, which is how someone can set up TornadoVM. Usually here in the past, we were going through all the steps that someone needs to do to build from source, but this is no more the case because we are able since December and version 2.0 to package TornadoVM, the technology and particular versions into SDK archives. And the archives are available first on the website of TornadoVM, as you see on the left part, but we have also successfully integrated TornadoVM as an SDK into SDK-man. So if you are using SDK-man, you can simply type SDK install TornadoVM, and this will install the latest version of TornadoVM and for OpenCL, which is the most compatible, let's say, backend for different devices and vendors. So how to install TornadoVM? In a sense, you type SDK install Java, and in this case, Temurin JDK 21, because TornadoVM, it is a technology that relies on JDK. It is a plugin for JDK. So we need to have the Java home exported. And once you have done this, you can type SDK install TornadoVM, and this will export a second variable that is required to run TornadoVM on your system. And this will be TornadoVM home. Okay, in this case, I think I can show you in the actual terminal how I'm using it. So as I said, on the top part of my screen, you see a terminal. On the bottom, you see an actual monitoring tool that monitors the CPU and the GPU on the right side if we run something, a GPU process. This is for later. But for now, let's focus on this terminal. We will use Temurin. We will use TornadoVM 2.2.0 OpenCL. And then we can do with Tornado, just to be sure. Okay, it is in SDK-man. We can validate the version that we have. We can validate the version of the JDK that is running, which is the Temurin 21. And we can also run a small test to identify the available devices on the system. So as we see here, it has detected the GPU that I have on the M4 Pro. And it pops some information like the global memory that's available to run and different hardware characteristics like the threads and the OpenCL version that it is available on the system. Okay, let's jump back. Okay, we just installed Tornado. We run Tornado devices. And in reality, we saw that we can actually run Tornado, and Tornado will be exposed with a class path of any application and a particular application. So if we go back to the terminal, we can actually run an example. So here's a matrix vector example that we have in the SDK, packaged in the SDK. So someone can reproduce it and run it. It will throw some information about the configuration. We may see also a spike here on the GPU because it will run on the GPU. And it pops up some useful metrics that runs using different implementations. For example, and add parallel notation, which we will show later in the matrix multiplication example, against Java implementation, which is the one that we saw earlier in the slides, the code snippet. And it has some useful information. But the most interesting part is that here we have the Tornado command. This, in a sense, it is an alias for Java, and it is a Python script that exposes useful information, useful flags. So it can be very helpful. So if we type Tornado help, we see all the options that are available. As we see, we have the devices that prints the actual devices on the system. We can have more information, for example, the print kernel that actually prints the OpenCL kernel in this setup. If we had PTX, it will print the PTX code. And if we had SPIRV backend, which is not, these two backends are not supported on M4. If we had them, then it will print the actual generated code on the console. Then we can enable the profiler, the Tornado Pulse profiler, as we said earlier, and decide the mode. And we have all this kind of information, including the print Java flags that prints all the flags, the JVM flags that are packaged in the Tornado command. Okay, we did it. We can try also one example. We can try to see the threads, the thread info that will print the actual threads that are deployed on the GPU at runtime. So as we see here, for particular kernels, we have different characteristics. So we have, for example, for this particular kernel, deploying 65K elements. So 65 is the global work size, and we are utilizing one dimension on the GPU. And we're also validating the results of the actual computation across all the implementations. Okay, at this stage, I would like to focus on the Tornado command. So we have Tornado, but in a sense, Tornado, as I said, is an alias for Java. So in a sense, we could replace it with the Java command and then just pass the ARC file that has packaged inside all the JVM flags that enable TornadoVM at runtime. And these are available through the TornadoVM home that we have exported earlier with SDKman. So someone could replace the Tornado command with this. Additionally, as I said, yes, Tornado Arc5 has JVM flags, and here we have just printed some flags that, as you see here, they are JVM options that enable the loading of the API implementation, runtime implementation, annotations, etc. And you can also append it with any other JVM flag that you want to use. So in theory, we can just replace Tornado command with Java TornadoVM ARC file, and I'm gonna try it as well so that we can see that it's exactly the same. So as you see here, it is exactly the same command. We have just added Java and TornadoVM ARC file, and the behavior is exactly the same. And we'll have the spikes as well on the GPU. Okay, let's move on. Now we can jump to the actual matrix multiplication example. In this case, we'll jump into the editor, the IDE. And I want to also show you the Tornado Insight, how it will work. So in theory, we will visit the matrix multiplication example to try to understand the TornadoVM API and how it is used for a matrix multiplication implementation. And then we will jump to see what is Tornado Insight. Regarding Tornado Insight, it is a JDK plugin that enables programmers to understand how the API works and what is supported. It has been open source. I think it's running for about 2 or 3 years and has been significantly extended through the P2 code and the Aero projects. And recently in December, when we released the SDKs, we also released a blog post that explains all the guidelines that someone needs to do in order to run the Tornado Insight with the latest SDKs. And now we are ready to jump into the actual editor. I have opened IntelliJ, as you see here. It is the TornadoVM project, and the branch is Tornado Inside Demos. What is interesting is that, as you see here, I am in the matrix multiplication 1D class. It is an example that we have. And we have defined some warm-up iterations, so it will run for 15 times. Then we express here the matrix multiplication. It is the canonical implementation of matrix multiplication. And as you see here, we are using the off-heap data types from TornadoVM API. And we have annotated the two outermost loops with that parallel annotation. This is an annotation exposed by the TornadoVM API, and is a way for programmers to indicate that these loops, they are candidates for parallelization. This means that this will annotate these loops, and the TornadoVM JIT compiler will have been noted that these are good candidates to run on different GPU threads. So someone can just run this on Java and just ignore that parallel annotation. And by adding this sugar, syntactic sugar, they are parallelizing the code. Now we jump into the main method. And as we see here, it is the same as I showed in the snippet earlier. We just create the objects, we randomize the input data, and actually here we are creating a task graph. A task graph is an object in the TornadoVM API that enables programmers to define what they want to run on the GPUs. So in this case, we create a task graph, we add a name, which is a string, S0, and then we define what we actually want to run on the GPU. So at first, TornadoVM API exposes this method, transfer to device, where we can explicitly select the data transfer mode. And in this case, we have first execution. So then we add the actual data that we want to transfer to the device memory, to the DDR. And as we see here, this means that in the first execution, we will copy the input data. So in a sense, this transfer mode reflects on read-only data. Then, if we want, we define the task. It can be one task or it can be many tasks if we want to chain different methods and execute them one after the other, so that one can produce data and the other can consume it, and the data can be persisted on the GPU memory. This is possible if we package them together in the same task graph. And as we see here in the task method, we just add a string again to identify the particular task if we have multiple tasks. And then we have the method reference, and then it is followed by the actual arguments of the method. And finally, we can define the transfer to host. So we're using this method to define the data that we want to copy back from the GPU memory. And in a sense, this will be the actual result data. And as we see here, we want the data to be sent in every execution. But again, there is an option as well if you want to do it under demand. Okay, here I have shown you how the task graph enables programmers to define what they want to run. But at this stage, someone can change something. So we can change the first execution to every execution. We can append and add a second task. So this is a mutable object. If we want to jump into the execution, we need to create a snapshot of this project that will freeze the actual shape of the graph. And this will create an immutable task graph. Then once we have a snapshot, we are ready to continue with the second object that someone needs to create, which is called Tornado Execution Plan. This object enables developers to define how they want to run on the hardware. So in this case, we pass the immutable task graph, we get the executor, and the executor can be configured with different options. For example, here we say with pre-compilation, which is an option that says trigger JIT compilation early before I execute. store the actual generated code in the code cache. And whenever I press .execute, as we will see here for the number of warming up iterations, whenever I press execute, the code will be already JITted. So in this scenario, we will run the warm-up phases, so 15 iterations to run on GPUs. Then we actually time it. Then we do the same for the sequential code that is running in Java for the same number of iterations. Then we time it. We create some metrics. And finally, we will dump the actual result and all the metrics. And we will also verify the code that the two results that they are identical. Okay, let's run it in the IntelliJ. So here we have the application. The only thing that someone needs to do is to edit configuration, add here the modify options, and add the VM options, as you see here, that has been already enabled. And this is the field where they actually need to copy paste the Java flags that I said earlier. So if you do tornado print Java flags, those flags are the exact text that you need to copy paste in order to run from IntelliJ here. Okay, and we are ready to launch the application. As you see here, it runs with Temurin, and we have successfully run it, and the speed up is almost 45x. But I wouldn't consider it a benchmark because of the number of iterations that we have warm up and the actual system that is running, where I'm sharing my screen and I'm running all the other processes as well. Okay, we finished with a matrix multiplication example. I think now it's a good idea to show you a little bit about the Insight plugin. So once you have IntelliJ open, you can click settings, you can go to the plugins list, and in the marketplace, if you type, you will find Tornado Insight. So if you install it, then you will be able to see that there is this kind of icon here on the right side. And a panel will appear where it will actually present any available tasks that are available on the open class file. So as we see here, we are in matrix multiplication, and we have identified matrix multiplication as a valid task. Now, what Tornado Insight does and how it helps programmer. It does two things. The first is syntax analysis, static analysis of the code inside the class. So as we see here, we don't have any errors. Now, if we move into the next class, which is the array list add example, we will see here that we have some data types in the method that we have used, the add parallel notation, that are identified as red. And this will come also with a message. As we see here, we read TornadoVM unsupported data type in TornadoVM. And this is because we cannot define objects that can change size at runtime here. This is because TornadoVM does not allow it, because GPUs, they cannot dynamically change the size. So that means that one method will be JIT compiled and needs to have static data sizes. And this gives a hint by using the plugin. Now, a second example is the throw exception. So here, as we see, we have a different class. We have an add method. In this case, we are performing division in parallel in different elements. As we see here, the task, the method that we want to compile is identified by the plugin, and we can actually trigger a dynamic inspection. This means that it will try to JIT compile the code, and it will print in the console the parallel implementation from the TornadoVM JIT compiler. This is a good news because dynamic testing was completed without error and without any exception, appearing in the console. So that gives a hint that the method is ready for deployment. Now, if we uncomment this throw exception statement, Then we see here that we have it has been detected as red, and this says incompatible thrown types with exception. And this is because in GPUs you cannot throw exceptions from a GPU kernel. So then the task has also been disappeared from the panel of the valid tasks. And one more example that we have is the dynamic array, where we have this method, the add. Here we have three primitive arrays and a for loop, and we create one array inside the method. Then we have the for loop, and we create a new object in every iteration. And essentially, we change the actual size of the object of the array. So this dynamically changes the size of the generated code. So at the compilation time, it will not be known the exact size. As we see here, the static analysis has not detected anything that is not normal. And if we click dynamic inspection, we will receive a message here that this is not implemented, then dynamically sized arrays declarations are not supported. So this gives a hint to programmers that something is wrong. Now, to validate this, if I change this to be a specific number, a constant, for example, let's say 4, and I do again a dynamic inspection, we will see that this has generated parallel code. And as we see here, the array that we are generating in every iteration, it is allocated in the private memory of the GPU and has the constant size of 4. Okay, now I think with that we can jump to the next part. More information about the TornadoVM and the API and all the data types and the examples that we have. They have been given in the deep dive talk that we gave in early October in DevOps 2025. And here is a QR code that you can scan and go into the actual YouTube video. So now I will move into the actual integration in Java projects. TornadoVM recently, since SDK version 2.0, it has been pushed in Maven Central. This makes it easier to be integrated in projects, so you can simply add these dependencies in your project. The first dependency regards the actual API. The second regards the runtime, the Tornado runtime. So if you just want to use data types and the task graph and Tornado execution plan, you can just use the API. If you want to query device information and this kind of information that are available at runtime, you may need as well the Tornado runtime dependency. What is interesting is that this enables Java users to build their applications and download the jar files from Maven Central. And this is important. So one case that we have built is GPU Llama 3. And this demonstrates that we can actually build more complex use cases with TornadoVM and deploy them. For those who don't know GPU Llama 3.java, this is an open source project that we have built in the Beehive Lab in the University of Manchester. In a sense, it is an LLM engine that enables the execution of queries and different models like Mistral, Llama 3, and more on local GPUs, so locally on our systems to run LLM on through Java. And this is a pure Java implementation that has been enabled with the TornadoVM API to run on GPUs. Here's the link and more information about the GPU Llama 3 project. It enables the switching between pure CPU to pure GPU inference, and it is implemented purely in Java with TornadoVM API. It supports GGUF model formats. Currently, we have here the list of the available supported models like Llama 3, Mistral, Phi 3, Gwen. Recently, we added support for IBM Granite. And we are working currently on Gemma. And what is more interesting as well is that we have integrated with LangChain for J and Quarkus, which makes it even more appealing. And it will enable, in a sense, it enables seamless hardware acceleration through this kind of platforms because you just integrate the dependencies in your projects and you take for free all the implementation that we have done in the GPU Llama 3 project. Now it's a good idea to jump into the demo of GPU Llama 3. So as you see on the bottom, we have this window with the GPU. Here we have the GPU Llama 3, which is cloned, and we are ready to deploy the actual example that takes the Llama 3 1 billion model and will run the prompt, tell me a joke, which is the typical example. So as we see here, TornadoVM changed the defined local size, and we get the generated output into the console. And we have some kind of metrics. Here we see the spike that it ran on the GPU on my system. And we're running currently with OpenCL on macOS. This is not a very optimized backend for GPUs on macOS because Apple has deprecated OpenCL support. But still, it gives us some good numbers. Like, for example, here we get a significant number of tokens per second, which is good. Okay, so I invite you to try the project, clone it, and try different examples and different models. And now I think we can jump to the actual integration with LangChain and Quarkus. So as I said earlier, you can simply use this kind of dependencies in the Maven projects that you have and you are running. And you can simply add the artifact ID LangChain for J GPU Llama 3 and the particular version that we support. We are currently working on support with JDK 25 for TornadoVM, which will unlock as well support for the latest LangChain for J distributions. And if you are using the Quarkus LangChain for J dependency, then you can consider as well to add the dependency for the Quarkus LangChain for J GPU Llama 3 implementation. And if you just want to add our project into your project, you can simply add the dependency to the GPU Llama 3 as a standalone. Now, what we wanted to create, it is a way to show you that GPU Llama 3 is integrated with Quarkus and LangChain for J. Therefore, we went through the docs of Quarkus and we found a very interesting implementation of a demo where they have this implementation of a summarization service. In a sense, this uses Jakarta Quarkus LangChain for J and invokes an LLM in order to create a summary version of an article that has been a text file. And here is the actual link of the documentation of this demo. So what we did, it was to actually take this inspiration of the implementation, the APIs, use exactly the same APIs, but instead use the dependency to GPU Llama 3 and configure the models that we have the support for. So if you clone this link, here is where we have the demo project for GPU Llama 3 Quarkus and LangChain for J. You can install Temurin, you can install TornadoVM, you can build a project and then run it into modes, chat mode and streaming mode. And let's do it. We jump into the terminal. This is the terminal. So as we see here, let's see SDK use 20 Java 21 point, yes, Temurin. SDK use Tornado 2.2.0. Excellent. And we are ready to deploy and run the demo. As we see here, we pass the device memory to be 8 GB and we will run the demo in the streaming mode. So This starts Quarkus. It has instantiated the application. This is the original input that we see here. And we started the deployment of the instantiation. So here we see some configurations. We see here the model of Llama 3 1 billion that has been selected. And these are from the application properties of Quarkus. And we see that the on GPU flag is true, which means that it will run on the GPU. And the instantiation is complete for the GPU Llama 3 streaming chat model. So as we see here, something is running on the GPU, and we start receiving tokens back from the LLM that is running on GPU Llama 3. So the output is that we need in a markdown format to receive a summary of the article. This particular article is about electric vehicles, and the LLM has structured the key points of the analysis of this article. And we receive the whole list of the key points along with one sentence that summarizes the article. And this is important because, as we see here, we run natively on M4 with OpenCL, which is not optimized. So we got a real-time response back. So running natively on high-end NVIDIA GPUs, it's completely much optimized and very fast. Okay, let's jump back. More information about the GPU Llama 3 project are available in YouTube from the DevOps talk that my colleague Michalis created. And yes, let's summarize the content. So TornadoVM in the past decade, it has been optimized across different use cases. They are listed and described in this link. It is important that with every new use case, we mature the technology and we optimize the compiler. And recently, we have had the first deployment with the Aero project and the integration with the European Space Agency Gaia mission. We have developed a Java native ray tracer implementation, which gives at runtime the rendering part to be offloaded on the GPUs. So it enables a very small and slow ray tracing implementation to be accelerated on the GPUs. And we have various integrations with machine learning frameworks and LLM frameworks to accelerate either in training or the inference, as you saw in the demo. So in our roadmap, we are continuing the work on optimizing the performance across different GPU vendors. We are extending the platform support with new backends and new integrations like Metal and for AMD. And we are creating AI-specific optimizations and some new features that are coming in the API as well to enable this kind of optimizations. We are working on compatibility with JDK 25, which is very important for us, and soon we will have a new release with that. And also, we are continuously monitoring many emerging features that are coming from Java and from open JDK projects like Project Babylon, Valhalla, and Leiden. So in summary, I just want you to take as a key message that Tornado is compatible with Eclipse Temurin for JDK 21 and soon for JDK 25. It enables native GPU acceleration of Java programs. It is a way to enable GPU-ready AI libraries for Java. And this is a fact that we saw with GPU Llama 3 demo and integration with LangChain4j and Quarkus. It is production ready, and we have a set of ecosystem that you can use and you can clone and try them to do performance analysis, deployment, or development. Finally, this work has been funded by EU research projects like Tango, P2Code, Aero, Encrypt, and in the past from Elegant and E2Data. So it is a work that is running for a decade. And with the last slide, I just want to say that it is not a one-person work. So it has been a team that's working for the past decade in this project. and we have many alumni that they have contributed significantly. And with that, I'm ready to take any questions and receive your feedback. Okay, I see some questions in the chat, right? Okay, hello. Will this talk be recorded for later reference? Yes, Adam. I think this talk will be available in YouTube soon. It's integrated in Quarkus. Are there plans to integrate it with Wildfly too? To be honest, I haven't tried Wildfly, but I mean, it is definitely an option that we can try and see if we can integrate. I don't think that there are any red flags regarding this. So I will say yes, we will give it a go. I think you are muted.
Thanks. Sorry. Thank you so much for that amazing presentation. Let's see if we have some questions before we close it.
Yes, definitely.
Thanks everyone in the audience also.
Yes, absolutely. I mean, feel free to give your feedback. Feel free to try it. And for anyone who will watch it later, we're very happy to contact us if you have any questions or if you are interested in trying the technology.
Yes.
Excellent. Great, Eduardo. If you have any questions or if you have any news, let us know regarding this integration in your project.
Oh, I think we have two more questions. I don't know if you saw it.
Yes, I just
Yeah.
from
Perfect.
Stuart about AI for agriculture. And yes, this is a comment and a question about plans towards JDK 25. We are currently resolving some corner cases into the integration with JDK 25. So hopefully soon, in a couple of weeks, we will have a new release with support for JDK 25 too.
Perfect. Well, I will add a link here with our next events, online events, for everyone if they would like to join us here. The crowdcast. All right. If it doesn't, okay, it doesn't look like there are any more questions. So I would like to thank you again, Thanos, for sharing your expertise and your time with us today, and for everyone attending. And I hope you have a great afternoon. Thank you so much.
Thank you very much. It was a pleasure. Thank you, guys. Take
Bye.
care. Bye bye.